question. We are going to be talking about momentum and impulse today. So if you guys want to open up this POGIL, it is 4 pages, but let's first talk about any information you might know about momentum. So does anybody know anything about momentum? Have they heard that word momentum before? What do we know about it? You can put it in the chat. You can tell me out loud anything you might have heard about the word before. All right, let's think about it in terms of like Newton's second law. Awesome. So Newton's second law does talk about momentum. When we're talking about movement, we can also think about it in terms of building up speed. Awesome. Amazing. So building up speed, or even like we talk about it in sports too, like that team has the momentum. They're like continually getting better and better. They're continually scoring. They're doing something. They're on the right track. They are moving. So when we talk about momentum, we're going to be talking about objects that are in motion. And so I am going to pull off my definitions straight from the physics classroom. It's a great website, and I'll put it in the chat for you guys to look at in terms of what I'm pulling my information from. So this first one is going to be just for momentum. And so let's talk about it in terms of sports, in the fact that we talk about momentum in sports, but we also talk about momentum in terms of physics. And we're going to talk about momentum a lot in terms of physics. So that's what we're going to be looking at the next couple days in the next unit, is to talk about momentum and then impulse, which we'll get to in just a second. But when we talk about momentum, we are going to be talking about when an object or a mass is in motion. So basic definition here is going to be that a mass is in motion. So when we talk about momentum, we're talking about something is moving. If it's not moving, it has no momentum. Is everybody okay with that definition? All right, got a thumbs up. Nobody stopped me. So if you look at that physics classroom source that I sent you, which is where I'm pulling all this information from, or giving you the exact definition they gave me from that online source, it talks about this formula that we can use to actually find momentum. So this P is going to be momentum. And so when we find momentum, we're talking about a mass in motion. So one of the 2 variables that we need this momentum to equal is going to be mass. One of the 2 things that we're going to be using is mass. The other one is our motion. And so when we talk about motion, in this case, we're talking about how fast an object is moving in a given direction. Or if you took your time and looked below, we're actually talking about our velocity right here. So we are going to use mass times velocity to give us that momentum. So our momentum is just our mass and our velocity multiplied together. Does anybody have any like general questions so far about this? All right. Have you guys heard the term impulse before? And what do we know about that term impulse? Doesn't have to be physics related if you've heard it before.
When like you do something on impulse, it's just out of like if you're at the store and you buy something, it could be out of impulse because like you want it then.
Awesome. So it's just like something random that you do at the moment. You're changing something, or you're adding something new to your life. You're changing what you're doing randomly, okay? So it's similar to what we're going to talk about in physics, because we're talking about momentum and impulse together. And so momentum is when a mass is in motion and it has this velocity. The impulse is going to be when that mass changes its velocity or changes its momentum. So here our change in momentum is what our impulse is, which is why that delta or that triangle is in front of our P or our rho technically, because it is the change in momentum. And if you're looking for that source, it is also now in your chat. So it's going to be our momentum, our change in momentum is the mass times the change in velocity. So this is going to be one way to write it, is our mass times the change in velocity. And we'll get to more information about more specifically how impulse is calculated, but it's going to be how our velocity changes for an object is what our impulse is going to be. Similar to when you go out and buy things on an impulse, on a whim, you're changing what you have, you're changing the fact that like, oh, it was random, I just bought that. Now this time we're changing our momentum, or we're changing how fast we're going instead of buying something. Does anybody have any questions on any of that? All right, so then let's look at table 1, and there are 5 questions below. I want you guys to go ahead and answer the first 5 questions. Go ahead and take a few minutes to answer those first 5 questions, and then we'll go ahead and go through it together as a class. So go ahead and take, do you guys think 6 minutes is enough time? Or how about we come back in 6 minutes and see where you guys are at in terms of those 5 questions? Guys, I did get a great question in the chat about worrying about sig figs. For this worksheet specifically, you do not have to worry about sig figs. If you choose to put them in sig figs, wonderful. If you don't, I wouldn't mark anything wrong. I wouldn't take off anything for this because it's just a homework assignment. I would, however, recommend that you do remember about sig figs because they are going to be important when you take your tests for your formatives and your summatives. So do look at sig figs, but if you are just trying to get through everything right now, don't worry too much about them. You can go back and fix things later, or you can just remember them for the future. All right, guys, it's been about 6 minutes. How do we feel? Do we have all the questions done, or do we want a few more minutes to work on it? A few more minutes. All right, so I'll give you, let's say 3 more minutes, and then we'll come back as a class and we'll go over the questions. All right, ladies and gentlemen, so let's go through some of these questions together. It's okay if you didn't get through all 5 because we're going to go through them all as a class, which means that you might be able to get them during this time. So first question says, what does that capital M mean with the masses given above? So who has an idea of what that capital M stands for? That M right there. Mega, perfect. So that capital M is for mega. So we have a megagram there, which means how many or how large is that? We can talk about it in terms of grams. We can talk about it in terms of kilograms. How large is that? All right, I got
1,000 kilograms.
Perfect. 1,000 kilograms equals 1 megagram. And that asked us which car is more massive. So is the blue car, the red car, which one's more massive? Based on that information, which one's going to be bigger? The freight train is going to be the biggest one. Perfect. Because it has no decimal points and it's in the mega, which means add 3 more zeros to get to kilograms. It is going to be our largest one. Number 2 said calculate the momentum for all vehicles and fill in the last row of the table. Which vehicle has the most momentum? So did anybody calculate the first one, that blue car? Who has a momentum for me? Anybody saw that one?
6,400.
All right, and then it's going to be kilogram meters per second. What about the green car? Did anybody find that one?
$12,000.
All right. Red truck.
$21,000.
Black truck.
$44,000.
All right. Passenger train.
$46 million.
All right, and freight train.
$160 million.
All right. Everybody like those numbers? Everybody like everything about those numbers? All right, I see 3 issues. Technically the same issue 3 times. Nobody else see the same issue I see?
Is it the labeling of the black truck and the trains?
What about it?
We wrote down kilograms, yeah, instead of megagrams.
No, I think he switched it to megagrams or to
Oh.
kilograms beforehand. So, but great try.
Is
Oh,
it the direction?
it is the direction. So we're talking about velocity here. Remember that speed and velocity. So if you remember from last semester or at all, that speed and velocity are two different things, because speed is a scalar value or a scalar quantity. It tells you a value or a magnitude. Velocity is a vector because it has a magnitude or a value and a direction. So we have to worry about the directions here. So we're going to actually add in the negative values, just telling us which way these objects are going. So those negatives just tell us the direction, nothing more, but we do need to make sure they're included during this time. Now, last part of question 2 said, which vehicle had the most momentum? Which vehicle is it? The freight train, perfect. It has the largest number, which means it has the largest momentum. All right. What is the effect of mass on momentum? So can you explain to me, what does the mass do to the momentum? And it says defend with 3 examples from your data table. Anybody have an idea about what the mass does to momentum? Even without data, who has an idea?
More mass means more momentum.
Exactly, more mass equals more momentum. All right, and there are 3 in particular that I'm looking at that help us determine that. 3 examples we could look at. Anybody else see those 3 that might be the easiest to compare?
The blue car, the passenger train, and the freight train.
All right, I like those ones. I am going to switch it up a little bit just so in terms of our evidence, I want to keep everything else constant. So if I was thinking about this in terms of trying to defend my answer, I'd look for everything else to be kept constant besides mass in terms of finding the momentum. So if we're looking, these 3 right here have the same velocity, which means the only thing that changed to find this momentum will be the mass. So if we look at our green car, the black truck, and the freight train, the only difference between those 3 is how much mass each of those objects has, which means if we can compare those, the green car has the smallest momentum, and it also has the smallest amount of mass. The black truck has the next smallest momentum because it had the next smallest mass. The freight train had the most mass, which means it had the most momentum. You can go in other ways. All of them should work out pretty much the same. You can tell those differences, but that would be the easiest way, in my opinion, because the velocity would be held constant, which means the only thing that changed was the mass. Anybody have any questions about that? All right. What effect did the velocity have on the momentum of the car or the train or the truck? Has nothing to do with it. All right, so let's take a look. Let's look at the cars just because they're very similar in mass. This one's 12,081 kilograms. This one is, if we turn this to kilograms, would be 12,005. So they're very similar in their mass, but their velocities are very different. It's twice as much velocity in that green car versus the blue car. And then let's look at our momentums. Did the momentums change based on those masses or based on the velocity change? Did the velocity doubled, it got twice as large. Does the momentum get bigger or does the momentum stay the same?
Bigger.
The momentum also got bigger. So again, the more velocity, more momentum. So if you wanted to give your evidence, you could cite the blue car versus the green car. Their masses are very similar, which means they can be held almost constant, but the velocity got a lot bigger, which means that our momentum, we can see, also jumped a lot, making our case that more velocity means there's more momentum. Any questions on 1 through 4? All right, number 5 says, how can a car have more velocity, more momentum than a train? So our example needs to be in terms of the blue car versus the freight train. So we already have their masses. One of them is 1,281 kilograms. One of them is 16,494 megagrams. How can I make my blue car have more momentum than my freight train? And there's going to be one example that kind of sticks out in my head. I don't know about the rest of you. Add more velocity. Okay, so give the blue car a lot more velocity. But if we look at it, it's going to take a lot of velocity. It's going to be a huge meters per second, which probably wouldn't happen with that blue car. So is there a different way we could change things so that the blue car has a larger momentum than that freight train? And I do like that thought process of velocity. Does anybody else have any different ideas? Make the freight train have a lower velocity. All right. So there's one example of a lower velocity that I'm thinking of. Does anybody else have that same thought about how to make that freight train's velocity low enough where we know the blue car will be having a larger momentum?
Changing direction.
Change the direction. Okay, so let's not worry about the direction aspect of it now, because the momentum, that direction just tells us which way it's going. But I like that thought. Okay, so let's keep going with more thoughts. Anybody else have a different idea?
Changing the mass of the freight train.
All right, we can't touch the masses. Those are going to be held constant, but I like changing numbers. And we're not making that blue car. Oh, somebody said it. Stopping the train. Perfect. If that freight train isn't moving, it's stuck. It's sitting still. What is our momentum for that freight train? Zero. Perfect, because the velocity would be 0, which would make the momentum equal to 0 as well. So if we stop the freight train, while the blue car keeps moving, the car has more momentum. All ideas were good, but I do like this one a lot because if we stop it, we know for a fact that our blue car would have more momentum since our freight train's momentum would equal 0. All right. The next page is talking about how time affects our object. So this time, if you look, it's talking about this guy who's getting punched in the face. And so hopefully none of you have ever experienced being punched in the face, and you never do experience being punched in the face. But now we can know the physics behind it and we can help ourselves out. So we have two pictures here. So one is this guy is rolling with the punch, meaning that his head is going in the same direction that the punch is going. So if the punch is moving toward the left, the punch is going this way, he is pulling his head to the left as well. In the second picture, this guy wants to face that punch head on. His head is moving to the right as our person's arm, the puncher, is moving their arm to the left. So one of them, the guy is going with the punch. The other one, they are colliding head on. And so then we're going to say that for these problems, that going to the left is a positive direction and going to the right is going to be our negative direction. So we only have a couple more minutes, but I do want to just talk about this one in terms of who do you think, which version of this guy is going to be in less pain? Let's call this version A and let's call this version B. Who do you think is going to be in less pain? All right, I got one answer, couple answers. Everybody's saying the same thing. Awesome, awesome, awesome. Version A is going to be in less pain. Why do you think that is? Anybody have any ideas? He's moving away from the punch, not towards the punch. Perfect. And so this actually ties back to the title of this section. And it talks about how much time, or how time fits into all this. So if we move away from the punch, you're giving that punch more time for that punch and that face to collide, making less force acting on that guy's face at a given second. When it happens all at once, it's instantaneous. There's no extra time to pad that punch, kind of like when you guys were running into the wall, or Jill and Jack were running into the wall with a safe versus a quilt. You're giving it more time for that collision to happen. It's making a softer or nicer or less painful attack on the body, whatever is going on. All right, guys, so you guys have these 5 questions, and then it goes through a lot of the math behind all this. So it talks a little bit more about the actual math and some different formulas besides just mass times the change in velocity. It talks about it a little bit more. And then there are practice problems for you guys to go ahead and do with this problem. Any questions on what you need to do?